Did you get a chance to look at midterm 3?
Yeah.
Look means just
I see question only. I haven't started.
other again.
I see questions only. I haven't started.
Yeah, I meant that. I mean, if you have seen the questions, did you feel comfortable about it, or
First question, first three, this page 1, 2.
that's okay?
This is, that momentum or something.
This one you're
I haven't gone through.
Number 4 scared me a little.
uh,
I haven't really delved into it.
yeah,
Cross product.
correct.
We
But
have
it is
learned
X
about dot product.
TXT, right? So then it's about moving things around. Think about it, and maybe month end, right? That's what it said. Okay. Next midterm. There will be one more homework due. And this is number I lost count. Homework 10, I suppose.
Yeah.
Homework 10, I'll make it due sometime during the last week, but then you can take extra time because I cannot make it due after Friday, so it's just not okay. So even if it is not legal, they shouldn't be doing it. So probably Friday, December. Friday, that will be due, and it will be on angular momentum. So like we have done harmonic oscillator, it will be angular momentum, and I might extend that homework just so that just to get some class. We missed a lot of classes, and we think I typically do differential equations in a completely different context, like I do Green's functions. Like here, I'm doing it using the quantum mechanical approach, which is a good approach. I might do it more rigorously another time, but I did it very differently. So this does give us the opportunity to do spherical harmonics in a very good context. So what I'm thinking is that the final exam might be just a take-home part where I'll just cover spherical harmonics. That's what might happen. So it may not be a usual final. It might be longer. That's the price you will get, but then you learn one more topic. That's the like I get to cover things on the using the excuse of final exam. Is that clear? Yeah.
So with spherical harmonics, is that closely related to calculus of variation?
No.
No. Okay.
No. Why did you ask?
I guess like honestly, I just couldn't remember because I've used spherical harmonics kind of in quantum mechanics before, and I think it was related to hydrogen atoms.
Yes.
And I couldn't remember the method, like the mathematical method that we used to solve it. And I don't know why I thought it was calculus of variation. It might just be the second order.
Yeah, I don't see now. There might be very clever way of using calculus of variations and saying that this is a minimized states in some sense, but usually that's not the way you would do it. The best way to say it is that like this, and this. I mean, I would have liked to highlight these things in this course. This is the right place, but again, there is a limited time in this course, and I have to be selective. And it somehow, I think Rob was, I think interactions with Rob motivated me to do a bit of quantum mechanics. That's how this went. But talking to what you're pointing out, so what happens is that we solve different, most of what we do in physics is we make a model. Sometimes it's called a law. Law is when it is applicable at a very universal level. So that's what a model becomes a law. If it is independent of material properties, it becomes a law. Right? Or an example could be surface tension, the contact angle that you have in surface tension, you can actually do a good, reasonably good prediction in that. But it is a material dependent property. For wood, it will be different. For metal, it will be different. You keep tweaking your model. Another example is cosmological model. For some things, it works this way, and then you say, oh, it doesn't work here, so you tweak it and this. So that you're able to explain various things, but with an if and only if. But there are certain laws like Newton's laws, Einstein's laws, which just work everywhere. And they are so fundamental that if something goes wrong there, most of what we know might have to be changed. So there is a lot of predictions we make using that. And if by any chance that goes wrong, there will be a lot of things at stake. It's not that it cannot be wrong, it can be wrong. It has been modified once by Einstein. So it can be modified again, but there is a lot of good things about it. Like Newton's law helps us in various things, and you want those features. It's not very sacred, but it has very good benefit. It's predictive. Like you say, you solve an equation, you predict it. And most of this thing is done using differential equations. You can see it right away that in Newton's law, there is a second derivative of position is equal to the force. And the moment you realize that for conservative forces, force is a gradient of energy, so that makes it a partial differential equation. So we are basically solving mostly second order differential equation, mostly, doesn't mean that. And then you ask, okay, how many are there? And it's surprising that there are only about a few differential equations we know how to solve. In fact, there is this Morse and Feshbach in 1930s. He wrote a very extensive book on mathematics, and he classified all these differential equations properly. It's not him, I think, all the people, or at least he put it into the textbook where he collects that. He concluded that there are 11 coordinate systems or 11 sort of differential equations you can. The basic way to say it is that there's 11 geometries where you can actually solve the problem. Like, for example, a circle, when you have a system where the coordinate system is on a sphere, that's a geometry. And that's solvable. The sphere is usually a very good geometry. A plane is a very good geometry. But cylinder comes out to be very hard, surprisingly, right? Most of the one-dimensional problems on a cylinder is easy, but if you go to electrodynamics, cylinder is hard to do. It's not exactly solvable. Like they don't separate. Basically, you want to separate your differential equation. When you write Maxwell's equation, your electric and magnetic field are coupled, right? And you want to be able to solve it. And most of the time, if you want to solve it in certain geometries, they just separate into two modes. When you think of photon has two modes, you want to separate them out. And not in every material that happens. That cylinder is not a very good geometry for various purposes. When it becomes a perfect conductor, it's okay. So in this way of doing it, so once you realize that there are only 11 geometries, then you say that, okay, that's interesting. So, and then if I further put it down for our master's level, all these 11 geometries involve ellipsoid, spheroid, those are slightly, these are parabolic coordinates. And if you remove all those slightly more exotic, I wouldn't call it exotic, like slightly more complicated geometries, the simple geometries are planar, like parallel plates, spherical, and cylindrical. These are the three basic geometries, and that's what we study them as rectangular coordinates, spherical coordinates, and cylindrical coordinates, right? You write any differential equation and put this, then you try to solve those equations. Whenever it comes to planar, so if you're doing physics or when you're trying to build models, you will, whenever you see a planar geometry, there is a translational symmetry. Right? Imagine our universe was completely planar, right? That means to say that I step one feet the other side, physics will not change because everything is symmetric if I move that way. So it should be the same. And that translational symmetry can be directly put into mathematical terms, and you would say that all the solutions can be written as Fourier, in terms of Fourier functions in that direction. Okay? So planar geometry immediately takes you to Fourier transform. So your solution will be Fourier transform, and that's e raised to I kx, right? So that's what you will see. That's one thing. Now, next you say that, okay, I said sphere. So now on a sphere, you ask what function is the most suitable on a sphere? What is a set of complete functions? Right? By now we know what is set of complete functions. Like Fourier functions are a set of complete functions. I can expand any function as a Fourier in a Fourier expansion, right? If there is a function that is defined on the surface of a sphere, which will depend on angle theta and phi. So I'm talking about, so you have a sphere and so there's an angle theta and a phi. So now think of a function which is just dependent on f of theta and phi. And then you say, what's the best or what is a suitable orthonormal set in the function space, not in the vector space, in the function space where you can expand this. And that's spherical harmonics. So clear? So for example, if you have f of x, right, you will immediately say, I want to do a Fourier expansion. So this is these are your eigenbases if you want, right? In the language that we are using, that's your eigenbases, and you're summing over k, that's your label k, right? And the components are f of k. Or that filled out. Is that clear? Like minus infinity plus infinity. Sometimes there's a 2 pi. At least in the way I do it, there's always 2. But it goes from here to there. So again, any function, if it's on a plane, can be expanded in an eigenbasis of Fourier functions. That's your Fourier function, and its components are this. Okay. Then you ask the same thing. What about f of theta phi? Well, how will you expand it? You expand it as a sum, because there's a finite angle theta goes from 0 to pi. You don't really need an integral. So you would do L equal to 0 to infinity. And this is your functions are y. So that's your spherical harmonic. Y Lm and theta phi. Notice the label here is k, right? I'm summing over k. X is your eigenbasis. K is your, I'm summing over all orthogonal states. Here, there are 2 of them, L and M. So I should sum over both L and M. So this M goes from minus L to plus L. You might have seen this in angular momentum, the hydrogen atom this shows up, right? And after that, the components, right? Whatever are your components, and you can call them, let's say F, right? So this is F tilde and Lm. That's it, because theta phi won't have theta phi. It should have K, let's yes, Lm. So that's your component. But any function, if I know this, I know this. Right? If I know this, I know this. If I know the components of a vector, I know the vector. So that's your spherical harmonics. You can often, it is sufficient to just introduce it, like Fourier functions. If you just introduce it, that's sufficient. The complete set, that's your orthogonality property. But sometimes it is nice to motivate it. You say that, okay, how to build this, right? And again, there's a nice construction of this using electricity and magnetism, or electrostatics actually. So as a charge, you make a dipole, you make a quadrupole, and each of this YLM is the field associated with a charge. That's your S state. Like hydrogen atom, this is SPDF, right? S is for a point charge, P is for a dipole, D is for a quadrupole, and higher. So it's a multipole expansion. Yeah, that's the right word. So this is called a multipole expansion. Right? So it's a good point to make. So that's it. That's something one. I think it should be done in a mathematics course like this, and one should have that idea by the time you get up. But I couldn't.
I have a question about that. So like we don't worry about the R, the radius of the sphere.
I said if there is a function of theta phi.
So I see.
Correct.
Yeah.
So if I have a function that is only on the surface of a sphere, so what you are asking is that what about the R, right? So you would say that in general, a function is R theta phi. This is another problem, right? So hydrogen atom, for example, right? So you would say that first, let me think of theta phi. If it is there is spherical symmetry, or it doesn't need to have a spherical symmetry. Spherical symmetry just makes it easy. So that's one possible expansion. Any function can be expanded. So first you will expand this. So now you do the same thing. So this is L equal to 0. So I'm expanding theta phi, right? So this is M equal to minus L plus L Y L M phi. And now I have F tilde, right? L M. But now theta phi I have taken care of, R remains, right? So that's your R. So this will be, your components will be R dependent. If I substitute this, if theta phi is not interesting, that if you have spherical symmetry, for example, theta phi is not interesting. So this will all go away. And the remaining part is your differential equation for R. Right? For example, if you have a parallel plate, right? And this is your Z direction. You'll immediately take away your X and Y. X and Y is not interesting. I want to remove that. So all the X and Y's will be in the Fourier function, and Z is the only interesting. In hydrogen atom, you do a similar thing, and the equation that you get is a Laguerre differential equation. Right? That's a Laguerre polynomial, and so. Does that answer it?
Yes, yes, thank you.
Okay. So let me proceed. So shall I begin? Harmonic oscillator? Yeah. So we did harmonic oscillator to a certain extent last time, but let's finish that problem. So the way we converted the harmonic oscillator problem. As any, so in the quantum mechanical sense, there is history. Okay. Yeah. So that is an H bar. So this is energy. H bar omega has the units of energy, and this is built out of two operators. Like we started with a harmonic oscillator, real one-dimensional harmonic oscillator, due to its as a description of a spring, and then made some change of coordinates and reached here. And these are operators. So in what sense are these operators? I say y comma y is 0, so that doesn't make it an operator. Y dagger y is also 0, but y comma y dagger is equal to 1. Right? And that's our equation. And then I introduced, so mainly if this is a constant, that's also a constant. This is the main piece in here, right? So we say there's an operator n, which is y dagger, y. That's often called the number operator. Called the number operator. And mostly because it's a diametrical quantity and it turns out to have the eigenvalues of eigenvalues as a number 0, 1, 2, 3. Also because later on in other contexts, this represents the number of particles also. But for our purposes, it's just called a number operator. Its eigenvalues you will see will be 0, 1, 2, 3 later on. But as of now, it's just, this is your operator and that's the constraint on that operator. That's the definition of these operators. And we would like to find the eigenvalues of this operator. And we would like to find the eigenvectors also. But whenever it is eigenvectors, it is convenient to do it in a basis. So we will find the eigenvectors associated with that. So the primary problem would be to find the eigenvectors. So n operating on eigenvectors and prime should give us the n prime. So we would like to know what is n prime to begin with. That will be our primary concern and the first first part of the lecture. And then we will actually project this. Once we know the eigen values, we at least at a symbolic way know that, oh, for each eigenvalue there is an eigenvector. But that doesn't mean that I really know the eigenvector. For knowing the eigenvector, I have to collapse it into some basis. Right? I have to project it on some basis, and we will project it on the position basis and actually be able to find all the solutions. So we also argued that n is Hermitian. So n is Hermitian, and the fact, and because n is built out of two operators, which is y and y dagger. So if I were to replace it with eigenvalues, this will be a complex number, and this will be the complex conjugate. That makes this necessarily positive. So we concluded that n prime, so this implies that n prime has to be greater than or equal to 0. Right? That's all we could conclude. So there is this differential equation, and we know that n prime is greater than or equal to 0. Question?
Does that carry like some physical significance with?
Oh, the Hermitianity?
Or kind of both, like the fact that n prime is greater than and equal to 0?
Yes, in the sense that, yeah. So are you familiar with harmonic? Like, do you know what's the solution going to be n prime? N prime will be 0, 1, 2, 3. So, right. So one can ask, who said that? Like, why 0? Why start from 0? Why not start from 0.5? Like, because typically what will happen now is that I'll introduce a ladder operator. I should be able to go up. I should be able to come down. That only requires the difference to be 1.
Mm-hmm.
So why not start with 0.75, go to 1.75, 2.75, 3.75, and then you'll be able to come down also. But while you're coming down, what will happen is that if I operate on 0.75, if I go down, I get a minus 0.25, right? That seems to be perfectly fine, right? But if I put this condition that it cannot go below 0, then that means that, okay, how do I restrict them? And the only way to restrict is that 0 has to be a state in this. So that conclusion, even though it seems to be a very, or it sounds like a very simple conclusion, but it's very central in this whole picture. Like, one should ask, is there any room left there that 0 is not an eigenstate? Like, suppose 0 was not an eigenstate, then what happens? Like, is there anything different that will happen? So was that your point? I mean, you were asking for the physics of that. So yeah, this will play an important role. Now it is greater than or equal to 0. And where are you going to say that prime is equal to 0 is very relevant, but I haven't said that yet. All right. So, yeah. So to investigate that, let's go back and see what about, let's just see how does this work, right? What is this equal to? So that's a number operator commuting with y itself. And remember, so there is a calculus associated with this also, in the sense that remember your Heisenberg equation, that any operator dy by dt is equal to IH bar, right? IH bar times y comma Hamiltonian. Like in this case, Hamiltonian is y dagger y, right? And that sort of gives you a calculus, in the sense that here we are talking about how can it change with time, right? The time dependence of this operator is the commutation relation. So in that sense, there is a calculus associated with that. And that I have been completely skipping here just because it's too short a course. So whenever you try to see quantum mechanics, think of what is a calculus. That's where the group theory connection comes in. You will hear that there is a lot of connection with group theory of quantum mechanics. So that calculus of these operators is the group theory. And that begins with this equation. And this itself, you can motivate it or derive it in a sense. But I'm skipping that. But it's not necessary here. But there is that undercurrent of those statements. Okay, so what is this equal to? Y dagger. So this is y dagger y times y minus y times, or actually do this as a operator, right? So this is y dagger y comma y, right, plus y dagger y times y, right? So it's a y comma y, we said is 0, so that goes away. Y dagger y is equal to -1, because y comma y dagger is 1, so this is -1, so that's minus y. So what does that mean? So let me write that more explicitly. So this is y dagger y times y minus of y times y dagger y is equal to minus y. And that's what that statement is. Let me operate this on the eigenbasis of the number operator. So this is equal to y dagger y. So that's your number operator, right? and yeah, okay, times y minus of y times y dagger y. Oh, I was operating on the number operator, forgot like that. So this is n prime, right, minus of y dagger y acting on the number operator. This is equal to minus y acting on the number. That's your number operator, right? Right there. And I know how it acts, correct? That's the only thing I know at this point. I know that the number operator acting on n prime gives me n prime. Right? That's your number operator provider. So I know this statement here, this I can replace with n prime, right? So if I were to replace that, so this tells me that y dagger y, which is the number operator n, so n times y times n prime minus y times n prime is equal to y. Is that clear? Move this to the left, and I learn that n times y. So I put a gap here. I want some parentheses now. I want to put this to the right side. So n prime is a number now, right? So it can go wherever it wants. So it is n prime plus 1 times n prime. Oh, there's a minus sign there.
Yeah.
That's what I was looking for. Thank you. So it's n prime minus 1 times y times n prime. Yes.
So we made it in prime instead of the regular n. That's because it was acting on the n.
Correct.
Okay, okay.
I use this. I cannot use it here because there is an operator in between. Right? So I cannot do that here, but here it is really acting on it, and I know the eigenvalue equation. Okay, clear? So now here is the important point. Now notice when n prime acts, we know that it's the state itself. It's an eigenstate, so it will give me back the state itself. But y is not, so n prime is not an eigenstate of y, or at least we don't know that it is an eigenstate of y. So this will actually change the state, right? This will move it. So there is a space, you take from one vector, right? It will make it go somewhere else, right? So this is no more an eigenvector. It's not expected, at least. Agreed? But now notice that what is happening. If I were to put a, so this is whatever the state is, right? So this is just to emphasize that that's a new state, okay? And that's equal to this. Okay. Now, if I were to read that, so there is an operator, the number operator, acting on a state. Don't forget that this is a y operator. There is a state, number operator acting on a state gives me n prime minus 1, a number, times the same state. What can you say about the state? It's an eigenvector of n. Right? Remember the eigenvalue equation, an operator operating on some state gives me back the state itself with a number in front of it. That's an eigenvalue equation, right? So this state is actually an eigenvector of n. In fact, it is this particular eigenvector, the eigenvector corresponding to this number, right? So this implies now, right? Notice I started from just one commutation relation, and the conclusion is that y is an eigenstate. In fact, this is n prime minus 1. Correct? That must be true. But are we missing something? Right? So this is correct statement, but there is a small detail in here that when in this equation, I can multiply a constant. Like if I put a 3 here and a 3 there, like 3 here and a 3 there, that's okay, right? So whatever the state is, I can multiply by a constant and not worry about it. So this is true only up to a constant, up to a complex number. Is that clear? So this is, I can put a constant here, n prime.
Real.
It doesn't have to be real, it can be complex, right? I can multiply by any number actually, as far as it's not an operator, as far as I can cross this n, right? It's okay, it can be a complex number, it cannot be an operator. So dn prime is some complex number. It'll turn out to be real. Okay, that's different, but as of now, we don't know. I forgot to move the camera. Clear? This is a statement that y starts from one eigenstate and takes you to another eigenstate. This is a standard thing you look for in a Hilbert space, because it gives you a way of evolving, like in the sense that this connects with what is unitary operator, but I will just in very passing actually mention this. So let's say that, so this is just I'm mentioning it to why this could be important. Okay, so let's go back to our vector notation just for a moment. So this is E1 plus E2 if that's equal to 1. Let me put it. Actually, this will also help you with your exam. Like there's one exam question very similar. Right, so there's E3 is equal to 1. So that's your three state eigen basis, right? And now let me construct an operator U, okay, which is E2 times E1 plus E3 times E2 plus 1, 2, 2, 3, 3, 1, right? So it's 1. Okay. And these are orthogonal. I mean, I did introduce the orthogonality. So there is a completeness and there is an orthogonal statement too. Now, in this notation, you want to keep this double dyadic notation. Right? What is U acting on E1 equal to?
E2, E3.
Yeah.
E2, E3.
Not E2, E3. Why E2, E3?
2 plus E3.
Like this goes to 0.
Mhm.
This goes to 0. Like E3 dot E1 is 0. E2 dot E1 is 0. This one survives. E1 dot E1 is 1. So this is E2. Correct?
Because they're orthonormal.
Because they're orthonormal. Yeah, right. Like I said, I didn't write it explicitly, so I'm using this plus if you want EI dotted with EI, EJ is equal to delta IJ. What about you operating on E2? What is that?
E3.
E3, good. You operating on E3 will be should be, pattern should be clear. That's E1. Notice what this is doing. I constructed an operator. I'm going from 1 to 2, 2 to 3, 3 to 1, right? What is Y doing, right? If this was 0, it will, sorry, it's going down, right? So if it starts from 10, it goes to 9, 9 goes to 8, and so on. That's the same thing. You can build this Y using this construction, like n bar. So this will be, if you were to have this, so this is, I want n minus 1, right? So this is n minus 1, n prime minus 1 times n. If I operate this on n prime, this will become 1, rest everything will be 0, and it will survive this. Right? Same thing here, E2, E1, right? E3, E2, 1 lower. Right? Same idea here. Right? So I can build that like that, right? And now you think of what is happening, like you have a coordinate system, I have 3 vectors. I want to now, this is discrete, so I'm jumping into this. So this is like a discrete jumps I'm making. If you were to do rotations, you would continuously do this, right? But these are discrete jumps you're making. So this is actually the calculus in a sense of this, or this is how you will evolve the system. Like in an energy eigenstate, you cannot go continuously, right? You have to start from 0, you have to go to 1, 1 to 2, like if you have energy state. So this is the way you can go. This is the only way you can go if you want. That's how you will jump from 1. So there's that you can think of it as an evolution operator, right? Unitary operators are the evolution operators. And yeah, you can show that this is unitary. Actually, I haven't shown that. Here you can show that U dagger will be go to 1. Those things you can show. So there's a kind of nice little things, details in there. Okay, with that digression, let's come back. So we have now concluded that if n is a eigenstate, like, or n prime is an eigenstate, n prime minus 1 is also an eigenstate, right? So if I start with 3, then 2 is also an eigenstate. In fact, if I start with 1.75, 0.75 is also an eigenstate. That's all we can say. 1 less is also an eigen value. Do the same thing with Y dagger.
I have a question.
Yes.
I actually don't necessarily see why it's negative Y here.
Oh, this negative Y, because this one was here, right? This one was 1. This is opposite.
Oh, so it's negative.
Negative.
Okay.
Right? Just algebra, like,
Sorry. Yeah.
right? That's all. And this is 0. So starting from this, I have to get this. I don't have any other choice, right? So, like I'm saying, it is very logical, right? If I say this is true, then this is a what do you call mathematical certainty? Like it is, it has to be true, right? It is a solid constraint we have in the system.
Thank you.
Okay. Okay. So let's jump to the same thing with Y dagger, right? So dagger Y, comma, Y dagger. It's like say number operator acting on Y dagger. So again, do the same thing first. What's the commutation relation? So this is Y dagger, Y comma dagger plus Y dagger times Y. This is 0. That's 1. So that's Y dagger. Same idea again. Expand this out. So that's an operator, but I want to write it like so it's Y dagger minus of the opposite Y dagger Y is equal. Operate this on the eigenstate of the number operator. So you have, let me write this as n times y dagger acting on n prime minus of y dagger acting on n prime is equal to y dagger and we again say, so this is now n prime, and I can put it on the right side, and I say n times y dagger prime is equal to n prime now plus 1 and y dagger prime. Exactly same logic again, that if n prime was an eigenstate, then y dagger times n prime is also an eigenstate. So this implies now, this implies that y dagger n prime actually is equal to c n prime times now n prime plus 1. So we have a lot of steps in between. What we have done as of now is, if I were to summarize, summary is that we said, we started by saying that n operating, so these we're looking for n primes. So we have agreed upon the fact that n prime, so first conclusion is that n prime is greater than or equal to 0. Correct. Next, we said that if n prime is an eigen value, n prime minus 1 is also an eigenstate or an eigenvalue, is also an eigenvalue. Strictly speaking, it has to be, right? There is no room there to escape that. Right? And you say that this is also an eigenvalue. And then you say that these three together has to imply, if these three are true, then n prime equal to 0 must be an eigenstate, because if it is not, this will not be satisfied. Right? But if all three are independently true, so if all three are true, and if n prime is not 0, that means 1, 2, 3 are not eigenvalues. Right? So it is 0.5 can be an eigenvalue, for example. So if 0.5 is an eigenvalue, then minus 0.5 is an eigenvalue. That disturbs that. Right? So non-integer, so this together, so these three imply that n prime cannot be non-integral. Right? It has to be integers. Like, in fact, it has to be positive integers, because already we have said has to be greater than 0. So all the fractions are out. And that gives the idea that why it's called a number operator. In a sense. Any questions at this stage? Yes.
So it's, I noticed like in the literature, like we're writing Y dagger Y is more common than writing Y dagger.
No.
Okay,
No.
there's no special.
No, there is. This is special. This is the number operator. Other one is not a number operator.
Oh, I see. Okay.
Other one is not a number. Other one is another. That's a Hermitian. Quote. Yeah, the other one is like the other one is not the same.
Okay.
I'm wondering. Okay, hold on. It is Hermitian. Yeah, it's. I'm missing. Y dagger Y and Y dagger are not the same, right? Because the fraction between them gives you 1, right? So they're not the same, and one is number operator, the other one is different. Yeah, whatever that is in fact that. What is the operator you're asking? Is there any physics associated with it? I think it is closely related, I would say, in the sense that it's probably shifted by 1. Like this Y that we are doing is probably shifting. Because I say that because okay, we do know that n is equal to Y dagger Y. So Y dagger, right, is n minus 1 actually. It has an operator, right? So this is n. So n minus 1 is Y dagger. So it's just shifted by 1. So that's the meaning of it immediately. Right. So it is also it's closely related. That's what I'm saying. But it is it's like the angular momentum, right? LZ and LX. They are closely related in the sense that they commute. LX, LY is related to the third one, right? In that sense, this is n minus 1 minus n. It's related. It's a commutation, but it's not exactly the same. And it's always the n that is worked on. But it's maybe the question you're asking, I can answer is that can I do the whole thing with Y dagger? Apparently, yes. Just this will become a minus half and so on. But all the eigenstates will be, yeah, then it won't be 0. Then your ground state will be minus 1. I think that's the point. Yeah. So it will be, so you can relabel the whole things, and that's perfect. Fine. Yeah. So eventually this is basically a label. And as far as you go to 0, that's perfectly fine. The ground state, Y hitting on the ground state has to be 0. It doesn't really have to be the 0 state itself. I can label it with something else and make sure that it goes to 0 and it operates on that. That's sufficient. Does that answer?
Yeah. Thank you.
Yeah. Okay, so n prime is non-integral, right? And the only thing we have at this, we are missing at this point is this constant, which is a matter of algebra. We can fix that, we can get that. So keeping time into picture, I'm going to skip that. Like it is basically algebra. I'll give you the answer using commutation relation, we can get that. But the next part is more interesting. That's why I'm going to skip it. Okay. So so using the same commutation relations, one can, it's a little tedious algebra, but not too tedious, like we have done much more tedious stuff in this course or in other courses, but a little exercise leads you to. So dn is actually equal to n minus 1. So dn prime is actually n prime minus 1, and that's the square root on that. Okay. And c of n prime is equal to square root of n prime. So what we have now, oh, by the way, the moment I said n prime cannot be non-integral, that means I know n primes now, right? It is 0, 1, 2, 3, right? So, so this immediately implies that n prime is equal to 0, 1, 2, and so on, right? Very cleanly it comes out. And the 0 is the important one. Once you get to 0, then everything else is right. So first you have to show that it's 0 is allowed. Right? So I know so basically I know all the eigens, I know the labels for all eigenstates, or all eigenvalues I know. Right? I know all eigenvalues, and I at least symbolically know all the eigenvectors. Like this is just a symbol, right? It just says that there exists an eigenbase and it satisfies completeness and orthogonality, but it doesn't know what is the functional form. Is it a matrix? Is it a function? Is it in which space is this? I don't know. Right? It's symbolic. It's an abstract concept that there is a eigenbasis which satisfies this. I don't even know whether it's a vector or it's a function. Right? I haven't said that, but it can be realized in any space you want. Right? This is just there exists an entity, that's this. Anything that satisfies this is a valid candidate. That's all we are saying. Right? I haven't said this is a vector or a function. So that's your eigenvector. And I have also given you some properties, that there is this interesting properties that y acting on n prime is n prime. Oh, did I do this correct? So this is n prime. And this is n prime plus 1. The way to remember is that y acting on 0 has to give me a 0, right? So this is going to give me a minus 1. 0. And y dagger. That's our information, and this is, I jumped that steps, but like I won't ask you either in the exam or anything, but it's a good exercise to finish it at least once in a life. At least at this point, I don't see any logical things you're missing if I skip on. Okay, so that's good. So this is the end of story. Like now I know everything about harmonic oscillator in principle, symbolically. But always we do things in a particular space. We would like to do it in a coordinate space. We would like to know the wave function. Right? So I would like to project this on x prime. Right? So the question is, what is x prime? Like that's just interesting, right? We know that these are Harmonic polynomials, right? Coming from Schrodinger equations, we know that. Can we get this from this description, right? Yes, we can. So let's at least get the 0th state. Okay. So we have this constraint that y acting on n prime, sorry, y acting on 0. Y acting on 0 is equal to, what is that? 0, right? So y acting on 0 is 0, right? That's an equation. Let me act on the position basis. So let me change this. It's still wrong there. So this is x prime acting on y 0 is equal to 0. right? I just, because I'm interested in this piece, right? Remember x prime 0. So I'm going to label this as psi and prime. That's what it said, wave function, right? Whatever is this projection, I'm going to call that this. Like whatever is the projection of this eigenvector in the position basis, that will be my wave function, right? And this particular, I can say that's the ground state. That's psi 0 x prime. That's your ground state. And so this has some information about ground state. This is a constraint satisfied by that ground state. What was your y? We want to bring it back, right? So y had some representations in terms of position and momentum, remember the first lecture, and that was I think I got to look up y. Yeah. So this was 1 over 2 h bar omega times square root of k x plus I e over square root of m. Do you guys have ENM class?
Yeah.
For this?
Yeah, we do.
Right. So keeping the ENM class in mind, let me simplify this. Let me set h bar equal to 1, omega is equal to 1, k is equal to 1, m is equal to 1. Simplifies things, but it's an exercise for you to put it back. Okay. What I will lose here is that I will miss the dimensional check on my equations, but helps. Okay. And P, remember, was h bar over I, right? H bar over I, which is 1 over I now. H bar over I d by dx, right? So 1 over I. So in that sense, y becomes 1 over root 2 times x plus d by dx. So my equation here is x prime times 1 over root 2. Since it is 0, I can get rid of that. X plus d by dx 0 is equal to 0. Clear? Good. Oh, I should also have been careful. This is x prime, that's x prime, right? Numbers. Yeah. In the position basis, these are all now actually numbers. It was x prime. I can bring this out. Because these are x primes, I can bring this out. That's x prime plus d by dx prime times x prime 0 is equal to 0. But that's my ground state. And I immediately have a differential equation for my ground state. A very simple differential equation, in fact. So I get x prime plus d by dx prime times psi 0 x prime is equal to 0. All of us know how to solve this. So d by dx prime 0 is equal to minus x prime 0. You can separate variables just symbolically talking. This is d psi 0 over psi 0 is equal to minus x prime dx prime. The integrate on both sides, and I have psi 0 x prime up to a constant c exponential minus x prime over 2. That's your ground state. You can normalize this, right? So normalization, so normalize this. Normalize means dx prime by 0 x prime star, if you want, this is a real actually, by 0 x prime, going all the way from minus infinity to plus infinity is equal to 1. That implies, so that implies actually, implies size 0 prime equal to, again, let's skip the details. What is size 0? I raised to, so this is 1 over pi 1 over 4. So the Gaussian integral, right? If you are familiar with it. The Gaussian function, is it familiar? Gaussian function is this bell curve you might have heard of. Right. At x prime equal to 0, it is 1, and then it dies down. In statistics, it plays a very important role. So this is called a Gaussian function. It's a Hermite polynomial of 0th order, right? That's a ground state. So that's the ground state. How do you get the next state? Use the y diagram, right? For the first thing, you get the second one, third one, and you can do it in one stroke. Why do it in so many pieces? You can do this in general, and we'll do that somewhere else. You will see that somewhere else. But the idea is this. Basic idea was find eigenvalues, symbolically know the eigenvectors, project it in. This is a projection on the position basis. I can ask, remember your homework now. There I was projecting it in the matrix, like a matrix representation. I can do various things. Any object that satisfies that algebra is a harmonic oscillator. So that's the nice part. So that's all. With all, when you skip all these things, you can really end it on time.
Right. This was really good. Thank you. I really like your notation.
Okay, this is not mine. Dirac's notation. 1930, yeah. And it's yeah, Dirac did it. Yeah, I mean, I'll recommend his book. When I started quantum mechanics, I did not read Dirac's book. It was not emphasized so much where I did my education. But now, when I look back, that is the best book.
And that's probably free now, right? I mean,
Yeah. I actually, if you go to my old websites, I give a link for that so that it's legal to put it, as far as I know. Now, these are very sensitive things that someone says that no, it's not. It is still under circulation, and it changes country to country. These rules change. But with Dirac's book, I took the liberty, and it's available in various archives. Yeah.
thank you.